Okay, so first of all, your first midterm grades. We had finished reading your first midterms, but we will not be putting your grades online because I know that some of you do not want to learn your grades. If you want to learn your grades, you can look at your papers after the class today from Vedat Tanrıverdi. I know that some of you have recitation hours after the class today. You will be able to look at your papers and also learn your grades also tomorrow morning and tomorrow afternoon. Tomorrow morning from Vedat Tanrıverdi, tomorrow afternoon from Vedat Ali Özkan. So you can we will announce the hours on the Piazza or LMS. We will send you information. So if you want to learn your grades, of course, yeah, they will be put online after your first exam. Yes. I mean, we didn't yet put them on the computer, so I don't really know the average. But my impression while I was reading them is that there is a group of students whose grades are around 70s and 80s. Now there are a significant number of students around 60s and 70s and 80s. There are some students who are 20, 30 range, but you see, there are around 100 students who are active in the class, 90, 100 students, doing homeworks, coming to the classes, taking the quizzes. But in the exam, there were like 127 students who took the first midterm. So there are about 30 students who didn't come to the class, who didn't do the homeworks, who didn't do anything about the course, but they came to the midterm. So I'm suspecting that that group is kind of the students who got 20 or 30 in the exam. There's also another group around 50s. Now the average, I expect it to be around 50 or around 40 or 50. That's the average. Yeah. Well, once we enter your grades into the computer somehow to get the average, we will let you know the average. Okay, the following weekend, your second midterm. Okay, so we will again have the midterm here. We are kind of, I mean, if you had taken the first midterm in this class, you will still be taking the second midterm in this class, but we are kind of trying to make some changes in U2 and U3, U1 and U2, because you see there are the 30 students who didn't come, so probably we can just make the exam in only 2 classes. So if you had taken the exam in U1 or U2, most probably you will be taking it in U2. If you had taken it here, you will again be taking your exam here, but we will again send you the list of students either today or tomorrow at 1:30. In the worst case, when you come to here, we will have the lists posted around, so you can see which class you are in. The exam this time will start at 1:30. I mean, you will not be waiting for me to start the exam, so it just takes too long. You will start the exam. After the exam starts, after you start solving the questions, I will go to the 2 classes and I will just explain the questions also in Turkish. Well, if you don't speak Turkish, most probably you will be taking the exam in U2. So that I will be able to explain the questions in Turkish only here. Any questions? It is 3 hours, it didn't change. It is 4 questions, but each question has more choices. So one question has 6 sub-questions. So on the average, it probably corresponds to 5 questions of the previous exam. Again, you have 15 points of bonus. It will be graded out of 100. So in principle, if you do everything, you will get 115 out of 100. Any other questions? And after the second midterm, we have this tea party. You are invited to the tea party. Well, it will be in the department on the 3rd floor. We will have some tea. Well, it's a tea party. And we will have some börek to eat. And you can relax, chat with us. Well, I will be there. Your assistants will be there. The department chair and the vice chairs, they will try to come join us also. The exam contains everything that we will be able to do until the end of these 2 hours. Anything else? Okay, so let's continue. We still have this rotation thing. Again, we have our wheel. Now, this is one example that we will not discuss, but I think it's an interesting example. So you see, there's a step over here. I have to exert some force so that the wheel goes over the step. I can exert a horizontal force. If I don't exert sufficient force, it will not go over the step. If I exert too much of force, it will just accelerate over the step. So what is the critical force that I should exert on this system, on the wheel? Yeah, in this, let's make it simple. Along this axis, I can also exert it over here, or on the axis. Now, how much force should I exert? Another interesting question is that, okay, so these two surfaces, as the wheel is rolling without sliding, well, that's the thing we will study here. This is rolling without sliding. There is some static friction force between the wheel and the table. So what is the static friction between the wheel and the table? Now, we don't know the magnitude of the static friction. You see, when we were discussing static friction, we know that the magnitude of the static friction is less than or equal to some static friction coefficient times the magnitude of the normal force. This is the only thing we know. Between 0 and this number. We don't know what. It will depend on the problem. It will depend on how much force you exert on the system, how much is necessary to balance the system. Now, how can we study that in this example? What is the coefficient of static friction? No, it will be constant, some constant, but definitely not 0, and definitely not mu s n. Well, we will see. Let's look at this problem. So we have this wheel, or you can just think it's a sphere. It's on a hill, and if you had ever dropped some spherical object on the hill or some money, and if you have been unlucky so that it will land vertical, it will just roll down. It will accelerate down and it will roll down. So what is the acceleration? So that's kind of what we will be studying. Or we can have an example. You have the coin. Well, it will be hard for you to see, but if you can manage to get it straight, it will accelerate down. Okay, you need something thicker. Well, there are various things we can do in this problem. Now, one thing you can ask is what will be its velocity when it is down the hill. So you start from some height h. So this is where your object is initially. It is at a height, let's say the center is at a height h. No, the bottom is at a height h. And then you know that it will start rolling. It will gain some velocity, some angular velocity, and some translational velocity. And when it reaches here, it will be moving with some velocity v. So what is this? It will have some velocity v, and it will also be rotating. What will be the direction of its angular velocity? Upward, you mean? Okay, so there is one guess. One says it's upward. Inside the blackboard, inside the blackboard. So why do you think it is perpendicularly upward? Or why do you think it is inside the blackboard? Okay, so the wheel is rotating in this direction. So the angular velocity you find by the right-hand rule. You just curl your fingers in the direction of the linear velocities of the objects on the wheel. around the rotation axis, and your thumb points in the direction of the angular velocity vector. So this is the direction of the angular velocity vector, and this is the linear velocity vector. And we know that the magnitude of V is equal to Y. But isn't this the velocity if it is rotating around the center of mass? In that case, this point would have this speed relative to the center of mass, no? So when we were saying that V is equal to omega r, we are saying that, okay, if I have this object rotating around the fixed axis, if you take any point at a distance r from the axis, its linear speed will be omega cross r. So that's what we did. But here we don't have a fixed axis. Or do we have a fixed axis? So what is the velocity of this point, of the point of contact? It's 0. So at this instant, my wheel is also rotating around this axis, which is at rest. It's the so-called instantaneous axis of rotation. At this instant, there is this axis of rotation, and that axis of rotation is at rest. So we can say that, okay, my object has some angular velocity for rotations around the center of mass, and the center of mass is moving with some velocity v. That is one approach. Or we can say that at the same instant, this point is at rest, and the whole thing is rotating around this point. Both will be valid descriptions. So if in this description, this is the center of mass at a distance r, so this point is moving in this direction with velocity omega r. And this point is moving in this direction. And it has the same speed as this point. And similarly, this point also is moving in this direction with the same speed. Now, this top point, this point, is moving with a speed omega times 2r. In this direction. So the further away you go from this rotation axis, their speeds will be increasing. So because I can describe the same thing as if it is rotating around this point. So it tells me that, okay, if I have an angular velocity omega, the center of mass is moving with a velocity v, but I know that this wheel is rotating around this point with an angular velocity omega. So a distance r away from this axis is moving with a speed omega cross r, omega times r. So this is my angular speed, my linear speed. Now I can talk about the total kinetic energy of this system. The total kinetic energy of my system is equal to one over 2 mv squared plus 1 over 2 I omega squared. Okay, I have this one. This is I center of mass. But I also have this one because the center of mass is moving. But I can write the same thing as 1 over 2 I omega squared. I is the moment of inertia for rotations around this axis. And as we had discussed in the previous day, this I is nothing but the center of mass moment of inertia plus mass times d squared, r squared. This is the mechanical energy of my system when it rolls down. Well, we know that the mechanical energy is conserved. What is the work done by friction force in this problem? Zero. Because there's no sliding. Since the surfaces are not sliding, the work done by friction force is 0. We will have one more interpretation of this thing, by the way. And in that case, let's come to that point later on. Okay, so we have the total mechanical energy, the total kinetic energy of the system at the end. Initially, if it's not moving, we just release it from rest. It only has potential energy. And the potential energy of the system will be, initially, this will be mg times h. Do you agree? Well, there are a few errors in this approximation, by the way. The problem is, okay, the center of mass position. The center of mass is not at a distance h. It is at a distance h plus this one. But a similar thing also holds at the end. Because you see, at the end also, the center of mass is at a distance r. Well, here, this height is not really r. It's less than r. But we will just make the assumption that this theta is sufficiently small so that this height is more or less r. So in the end, this is my kinetic energy plus I will have the mgr from the potential energy. And there I have mgh plus mgr also at this term. And they will just cancel from both sides. Still, I'm making one assumption, though. I'm just approximating this height by r, which is true only if theta is sufficiently small. Because we will be doing the same approximation in the, we will be solving this problem from various approaches. This is the energy conservation approach. And then we will just calculate the acceleration. From that approach also, in that approach also, we will be neglecting the difference. We will be assuming that theta is small. So this approximation works good enough. So just ignoring the mgr, the same in both sides. The initial mechanical energy is mgh. The final mechanical energy, or let's just add mgr. The final mechanical energy is 1/2 I center of mass plus m r squared omega squared plus mgr. So they just cancel. And you obtain omega squared is equal to 2 mgh divided by I center of mass plus mr squared. And from here you can calculate its linear speed at the end. So the linear speed is just omega r, which is equal to square root of 2gh times square root of 2mr squared. Now mr squared divided by I center of mass plus mr squared. So this is the final speed of my object. Now, if it was a point mass, we had already studied the point mass sliding down an incline, and we know that in that case, the speed at the end of the incline is 2gh. Now, we also have this additional factor because of the center of mass. For a point mass, the moment of inertia around the center of mass, this is 0, so this factor is 1, this square root. But since my object has started to rotate, its final speed is reduced. Well, this is less than 1. So when it reaches the bottom of the hill, it has a less speed. smaller speed. Well, that is kind of understandable because initially it had only the potential energy, and finally, okay, there is this translational kinetic energy, but there's also some of the initial potential energy has been converted into rotational kinetic energy. So that's why the translational speed is less than if it was not rotating or if it was a point mass. This is one approach from the conservation of energy. Now let's calculate the acceleration of the system. We know the forces acting on my system. Well, this is my system, and we had just discussed that if it's rolling without slipping, this point is fixed. So we can just think that the whole system is rotating around this point. At least at this instant, it is rotating around this point. The forces acting on my system, well, there is the weight, mg. There is also the friction force. There should be some friction force, because if there is no friction force, it will not start to rotate. There is the friction force, there is the weight, and those are the only forces I have. So what is the torque acting on my system? The torque is equal to mg times r times sine theta. What will be the direction of the torque vector? Well, start to get something out of the plane of the board. Outwards. Okay, so that's a good guess. Why outwards? Well, the torque, remember, it is r cross f. R is the point where the force acts. Well, F is your force. Out of the blackboard. Parallel to the blackboard. Okay, so let's see. This is the x direction, this is the y direction, and this is the z direction. Z direction is in this way. So there are 6 possibilities, no? Either x minus x, y minus y, z minus z. We already heard the 3 of them. Any other opinion? Y minus x. Okay, so you are saying that the torque is in this direction. Why? Because the force is, okay, minus z. Why? Oh, 1 minute. The radius vector is this one. It is not downward, it is upward. Plus z. How do you get plus z? Okay, minus z. Okay, fingers in the direction of r. I want to see the fingers in the direction of the r. I want more fingers. Keep your fingers up in the direction of r. So the r is not in this direction, r is in this direction. So this is r. F is over there, so your palm should point in the direction of F. R is not like this, R is over there. F looks towards, your palm looks towards F. So F is over here, this is your force. So F, R cross F, and your thumb points in the minus z direction. So the torque is, this is equal to mgr sine theta in the minus z direction. Well, the torque, we know that the torque is proportional to I times alpha before you had said that the omega vector is pointing inside in the minus z direction. Initially the omega vector is 0, so finally it has some omega vector in the minus z direction. So the angular acceleration has to be in the minus z direction, which means the torque has to be in the minus z direction. So now things are kind of consistent with each other. Well, this moment of inertia, by the way, since we are considering rotations around this point, this moment of inertia is for rotations around this point. If you compare it with the, well, that I is this I over there. It's not the moment of inertia around the center of mass. So this gives us that alpha, the magnitude of the, well, the component of the angular acceleration in the z direction should be minus mgr sine theta divided by I. This should be the angular acceleration of my system. Of course, in this description, we are assuming that my system is rotating around this axis, and the torque is created by its weight. We had in the last, on Tuesday, we had also said that if you have a system that is also rotating and also translating, you can describe it as a rotation around the center of mass plus translations of the center of mass. So we can just consider this object as if it is rotating around the center of mass. Now, well, this is one result we have. We know that its angular acceleration has to be given by this expression, which is also equal to mgr sine theta divided by I center of mass plus m times r squared. And before continuing, what is the tangential acceleration of my system? If this is its angular acceleration, the tangential acceleration of the center of mass. It is just alpha times r. So it should be equal to m r squared divided by m r squared plus the center of mass times g sine theta. Now, if you remember our result for the acceleration of a point mass on an inclined plane without any friction, it was only g sine theta. Now, since my object is rotating, I get this additional term, which for point mass, if I center of mass is 0, it just reduces to 1. So the tangential acceleration for a point mass is again g sine theta. So this is just the consistency check of our results. Yes? No, the torque is r cross f. So if you change f and r, then the sign changes. So the torque is always r cross f. Now let's look at the system as if it is rotating around this point. If it is rotating around the center of mass, well, the weight doesn't create any torque. The only torque created is due to the friction force. And that torque is the torque around for rotations around center of mass is equal to it is R is just R. F friction. The angle between the two, 90 degrees, sine of 90 degrees is 1, so that is our torque. And this should be equal to I center of mass, the moment of inertia around the center of mass times the angular acceleration around the center of mass. But remember, angular acceleration, just like angular velocity, is a property of the system as a whole. If my system is has an angular velocity omega around this axis, then it also has an angular velocity omega around this axis. So it doesn't change if I change my axis. So I have the same alpha. R times F friction is I center of mass times mgr sine theta divided by I center of mass plus m times r squared. So we know that the friction force should be equal to I center of mass divided by I center of mass plus mr squared times mg sine theta. So this is the friction force that we need for the wheel to rotate without sliding. So if this wheel starts, if I move this wheel and it doesn't slide, it means that there is sufficient friction to start my wheel to rotate, and this is the necessary friction force. If this was a slippery surface with very small friction, in that case, I wouldn't have enough friction force, so my wheel will not start rotating. So it will just slide over the surface without starting to rotate. And the condition for me to have such a friction force is that this force should be less than mu s times the normal force. What is the normal force in this case? Doesn't it change because of it? Because I mean, if it wasn't a system with a rotation, we know that n is mg cosine theta. But we also know that if it's a system without a rotation, then the acceleration would have been just g sine theta. But we know that it has been changed. The acceleration is not g sine theta. It is less than g sine theta because of rotation. So don't you expect any change in this n? Why not? I mean, why this acceleration was different, but this acceleration, this force doesn't change? Well, that force changed, this one didn't. The wheel is not really at rest. This axis is at rest. This point is at rest, okay? The normal force. Well, can't we make the same argument for the acceleration? Why not? Good point. Okay, that's one explanation, one proposal, let's say. One answer. So your friend is claiming that, okay, the normal force is a property of this point only, and this point is not rotating. So this point doesn't know whether the wheel is rotating or not. So the force that this point exerts shouldn't be affected. Good point. Anything else? Heza? Yes. Okay. So that is another argument against the previous argument. Well, let's look at this thing from another point of view. This is my system. Up to now, we always said, okay, this is our system. We didn't specify what is inside and what happens inside. We just said, okay, this is our mass. Well, this is our mass. What are the forces acting on my mass? This is rotating. So we had just said that there's friction force. This is a friction. This is the friction force. There is the weight. There is the normal force acting on my system. And we also know that mass times the acceleration of the center of mass should be equal to the total external forces acting on the system. This should always hold, whether my system is rotating or not. This always holds. So we see, okay, the acceleration of the system is reduced if it is rotating. Well, that is kind of natural, no? We have this additional friction force acting on my system. I have this weight, which has a horizontal component, but there's also this friction force, which is slowing it down. So the acceleration of my system is, of course, less than g sine theta. We had obtained this result, g sine theta, assuming that there was no friction. But now there is friction, and that is how much friction we have. So it slows down. But that friction force is in the horizontal direction. It doesn't affect the normal forces. Well, the net force in the normal direction, in this direction, is just n minus mg cosine theta. And the center of mass of my system is not accelerating in this direction. So this should be equal to 0. So the normal force has to be equal to mg cosine theta. This is my normal force, so it doesn't change. But your friend also had a good point, by the way. Physics is local. So if you are talking about this point, it only knows its nearby points, not this point. And if you just take a point on the axis of rotation, you cannot really say that it is rotating or not. Rotation of a point is not defined. So let's continue with this. We know, okay, we know the normal force. This is the normal force. We had already obtained what friction force we need for the system to start rotating without sliding. So this just tells me that this friction force has to be less than the coefficient of static friction times the normal force, which is mg cosine theta. If mu s is large enough to satisfy this relation, well, capital M. If mu s is large enough to satisfy this relation, in that case, my wheel can just roll down the hill without sliding. If mu s is not large enough, then it will start sliding. Yes, your question. Which ones? Well, this torque causes my system to rotate around this axis. That is the torque for rotations around this axis, this torque. And this torque is it is the torque for rotations around the center of mass, around this point. So that's why those two are different. But of course, both torques should give me the same angular acceleration. Because the angular acceleration of my object for rotations around this axis and the angular acceleration for rotations around this axis, they are identical. Because the angular velocity at every point of my object is the same. Questions? So we know the tangential acceleration of my system, how much my system accelerates. Well, the next question is, how long does it take my system to go from this point to the bottom of the hill? By the way, in this description, there is a friction force acting on my system. And the friction force in this description is doing some work on the system. There's friction force, my system is displaced, so it is doing work. So the kinetic energy of my system is decreased. But remember, in this description, the only kinetic energy I define is the linear translational kinetic energy, not the rotational kinetic energy. In this description, Rotational kinetic energy is what we call the internal energy of the system. So friction force, okay, it causes me to lose energy in the sense that some energy is converted into internal energy. In this description, that internal energy is the rotational kinetic energy of my system. In this description, okay, I define my kinetic energy as both the linear translational kinetic energy plus the rotational kinetic energy. In this system, the sum of these two energies is conserved. There is no other internal energy involved in this case. Now, we had found the angular acceleration. So how long does it take for my system to go from here to there? 1/2 is tangential acceleration times t squared should be equal to h/sin theta. So this is the distance in the horizontal plane that my system covers. Well, this is how much, with constant acceleration, this is how much my system moves in a given time t, assuming that my system starts from rest. And that is my question initially. At here, the sphere is at rest. So it just starts rolling. You can obtain the t, 2h/8 tangent acceleration times sine theta. This is my t. Well, I know the acceleration. This is my tangential acceleration. At the end of that time, its speed will be just the tangential acceleration. This is the square root. The tangential acceleration times the t. Well, you can just do the algebra. You see, this is the time is twice the h divided by a times sine theta. And the velocity is a times t, and you just get this result, the final speed at the end of the hill. And, well, did I erase it? Well, it's exactly the same result as before. So this is its speed at the bottom of the hill using the torques and the acceleration, and it was the same result that we obtained by using the conservation of energy. Now the question is, in the conservation of energy, we made some assumption that this theta is sufficiently small so that we could neglect the difference of this height from r. Where did we make the same assumption in this discussion? We made almost the identical approximation in this derivation. How did we do it? Well, you have 10 minutes to figure out where is our approximation. This derivation was not exact. Somewhere we had assumed that this angle was small enough. You can go for a break.